All right, thank you for coming. We're session 4 of the Applied Data Science Invited Speakers track. And yet again, we have an amazing line of speakers. It's my immense pleasure to introduce Marc Najork. He's a distinguished research scientist at Google DeepMind, working on new techniques to make it easier for people to obtain relevant and useful information when and where they need it. Marc is interested in using Gen AI and language models to answer questions directly, rather than inferring users to relevant resources. Direct answers represent a major paradigm shift in information retrieval, affecting the user experience. Prior to joining Google, Marc was a principal researcher at Microsoft Research and a research scientist at Digital Equipment Corporation. He's an ACM fellow, an IEEE fellow, a AAAS fellow, and a SIGIR Academy member. Today, he's going to talk about generative information retrieval, and without further ado, Marc.
Thank you, Faisal. Thank you, everybody, for making it back from the coffee break. Coffee is very tempting, and it's a very tough act now to follow such great invited talks as we just had in the previous session, so I will do my best. So today I would like to tell you about the emerging field of generative information retrieval, and about the confluence of traditional information retrieval and natural language understanding. This is a rewarm of a keynote I gave 2 years ago, and the main message you should take out of this is that the sky isn't falling and information retrieval is as alive and as exciting and as thriving as ever. Gen AI is not going to do away with traditional information retrieval. Much of the talk is looking back, and then the tail end is looking forward, and I hope that will be somewhat inspirational. So before we get started, I would like to present some important disclaimers. So first of all, while I work for Google, I cannot possibly speak for the company. They will immediately fire me if I try to do so. So anything I say in this talk is my personal opinion. None of it should be interpreted as an announcement of any future Google products or anybody else's products. And then finally, some of the work I will be talking about is my own work, but much of it is by colleagues at Google or colleagues in the research community at large. So I really want to paint a picture for you how information retrieval and natural language understanding have evolved and eventually found a happy union. And I want to show you how search will move from providing lists of results to actually directly answering questions. Okay, so, sorry, wrong direction. So what do I mean by providing answers? Over the past 3 years roughly, there has been a proliferation of commercial question answering systems. Here on the left, we got Google AI Mode, and then 10 other systems, and this picture isn't complete, and every couple of weeks a new entrant is entering the scene. It's fair to say that we live in a Cambrian explosion of such question answering systems. So what is the value proposition of these systems? The value proposition is that they lower the cost of getting answers to questions. And the cost is a mental cost, a physical cost as in typing, and a time investment. They are more direct than traditional information retrieval systems, and that has some advantages and some risks. Among the risks are that users may become overly trusting in the results. They might not fact check if the results are actually true, and they might become more and more reliant on such systems. And again, on direction. So here's the outline of my talk. So first I'm going to review the evolution of information retrieval systems, then I'm going to talk about language models for question answering, then I'm going to talk about retrieval augmented generative question answering systems, which is what all of those things were on the previous slide. I'm going to talk about tool use, I'm going to talk about reasoning abilities, and then finally I'm going to talk about how Gen AI is affecting the web ecosystem as a whole, and Google in particular. And then I'm going to conclude with some key takeaway points. So now, first I'm going to talk about the evolution of retrieval systems. Information retrieval is a very old field. It started in the early 1950s, and it was really an outcome of the end of World War II. At the end of World War II, a lot of classified technical reports were declassified, ended up in libraries, and librarians were overwhelmed in bringing those things to an interested technical audience. And computers, which were a very newfangled thing at the time, were, of course, brought to the rescue. And so in those past 70 years, the basic retrieval paradigm has remained essentially unchanged. An individual with information need frames this information need in the form of a query, submits the query to the retrieval system, gets back a list of references to documents that are likely to satisfy the information need. Hopefully those documents are in a relevant ranked order, so the user doesn't have to scroll down the list too far. And ideally, they should have a short excerpt of relevant passages so the user can decide without opening the document or without going to the bookshelf whether or not the result is relevant. So fast forward to the mid-1990s, the advent of the web and of search engines. On the very left is a screenshot of Alta Vista. I actually worked on Alta Vista around that time. You can see there is a query box and there is a list of results. At the very far right is Google, taken a couple of weeks ago, and you can see the experiences hasn't changed that much, right? Yes, there are now info boxes that give you information about particular topics. There are special experiences for some queries like the weather today, or what are the movie show times, or what is a stock ticker. But by and large, it's still 10 blue links. And I should also say this is changing. There are two new generative experiences in Google search. One is called AI Mode, and the other one is called AI Overview. We're going to talk more about that. So what is the problem with 10 blue links? So as it turns out, there is a cost to using these retrieval systems, as I mentioned before, in terms of the mental load of mapping information need to a query, of typing in the query, of scanning the list of results and deciding what is relevant. Andre Broder and Preston McAfee refer to this as the Delphi cost of information gathering. Here on the left is a screenshot of an archive paper that I encourage you to read. It's a very elegant framework. It explains a lot of the research that has been done in information retrieval through the lens of all that research being directed at lowering the Delphi cost. So for example, research on ranking is about lowering the time cost. You don't have to scroll down the list of results so much. Research in snippet generation is again about lowering the time cost. You can decide if a result is relevant without clicking on it. And research on synonym expansion is about improving recall, so you actually find the stuff that you care about. You don't have to reformulate the query yourself. So there are two very simple reasons why information retrieval system evolved the way that they did. They are actually very effective at guiding people to the needed information, and we know how to build them. It's always very important. And this is due to two key ingredients. The representation primitives in early information retrieval systems were individual terms, and the retrieval mechanism was inverted indices. And there was a paper by Taubig, Will, and Wachtel in 1952, shown here on the screen, that suggested to actually index all the words in a document. Initially, they only indexed the title and the abstract. They couldn't actually store the whole document in a computer. They called this the unit term coordinate indexing, and a lot of research has shown that this is a very, very effective way of locating relevant information. The other actually, this is the research here. There's a study by a fellow named Cyril Clevedon that compared the unit term system against all the other information retrieval systems which were extant in the 1950s, and found that it beat those systems. Those other systems were based on hierarchical document classifications, typically done by a librarian. So think about the Dewey Decimal Classification System. A human comes around and places the document in a hierarchy. And just index it by terms is way more efficient. Okay, so the other key ingredient is the inverted index. Inverted index at a high level is just a mapping from words to the position in documents where that word occurs. And you can implement this very efficiently, right? You can map these posting lists to disks, you can keep them in main memory. They support complex queries, you can do conjunctions of terms, you can do disjunctions of terms. You can ask for proximity to two words that occur close to each other. You can issue phrasal queries that words are really adjacent to one another. You can even do negation. And you can compose those things. We have a very rich query language. And as an extra benefit, the inverted index also supports simple scoring functions like TF-IDF or BM25, because you know how long the postings list are, which is the key number to remember. So because this inverted index is so well suited to uniterm style retrieval systems, there has been oodles and oodles of research on how to optimize it, on compressing the index, on updating the index in real time, on stratifying the index across multiple tiers. So you would have like a super fresh tier and a not so fresh tier and then a giant tier, and about sharding the index across many, many machines. So let me just quickly recap the key properties of this lexical approach. Terms are completely uninterpreted. They are basically a number, right, a hash. Two terms with similar semantics are completely separate in this model. So, for example, turtle and tortoise are synonyms in English, but they will have separate postings lists. To cope with this limitation, most traditional retrieval systems have a stage where they will do a synonym expansion to say this query could be about turtle or tortoise or another synonym. Boolean and proximity operators can be implemented very efficiently just by traversing the postings list in lockstep. It's easy to scale those indices to large corpora by sharding them, for instance, by document and distributing them over 5,000 machines. It's easy to replicate the index if you want to have fault tolerance. It's straightforward to update the index just by starting a new tier, and then periodically you can merge the tiers together. And the inverted index is a perfect match for Thornton's term vector model that says that the importance of a term is inversely proportional to the frequency of that term in the corpus. And it's easy to maintain signed information on how many documents contain a given term. So we can easily compute metrics such as TF-IDF or BM25. On the other hand, the inverted index is not well suited to find documents that are semantically related. Okay, so here's the architecture of a classical web search engine at a very, very abstract level. The system has two parts, an offline component shown on the left, which is responsible for acquiring content through a web crawler, and then A, storing it, and B, indexing it. There is two repositories in the middle, the corpus of all the crawled web pages and the index of all the pages. Index as in postings list. And then on the right is the online component, which consists of a front end. Users come and submit a query to the front end will go and first issue that query to the index server, get back a bunch of document identifiers of documents containing the query terms, and then go to the corpus server, get those documents, extract snippets, present the results to the user. Okay, so in 1957, a fellow named John Rupert Firth, who was a linguist and is known as the father of distributed semantics, coined the very pithy phrase, "You shall know a word by the company it keeps." Words are, in fact, not distributed at random across the documents in the corpus. Semantically related terms do tend to co-occur. And this property is well known to the information retrieval community. For instance, latent semantic indexing is all based on that. On the other hand, Thornton's vector space model assumes that terms are distributed independently. And that's, in my mind, a fine example of that the tool that you have, namely the inverted index, shapes your thinking. So in around 2010, 2013, I guess, there were two breakthroughs that shook things up. One was the invention of word embeddings and data document embeddings, which capture semantic relatedness between words, sentences, paragraphs, or entire documents. And the other one was the maturation of vector databases that make it easy to get documents or vectors that are close to a given vector in a high-dimensional space. On the left is a paper by colleagues at Google that introduced the concept of word embeddings. So in this work, each word is represented by a fixed-sized vector of real numbers. The learner is presented as a word and its context, so think 5 terms to the left, 5 terms to the right. The training objective of the learner is to learn a word representation that is good at predicting the context words. This captures the essence of the first idea that semantically related terms have embeddings that are close in embedding space. And there are many open source implementations of word embedding trainers. I listed a few here. There's Glove from Stanford. There's FastText from Meta. There's the Google one. So if you were to build a search engine based on that, it would look like this. Sorry, again, the wrong direction. A follow-on paper, again by colleagues at Google, generalized word embeddings to variable length sequences of word, sentences, paragraphs, or documents. The representation of these variable length sequences of word is still a fixed length vector. And similar sentences or similar documents are close together in embedding space. And so this provides us with an alternative document representation to Thornton's term vector model, where you have giant vectors with ones for all the word occurrences that occur in the document. So this captures the soft semantics as opposed to the hard semantics that is captured by a purely lexical scheme. Okay, so if you train a neural network on this, then that network will, if you train a neural network on a large collection of documents, the network will capture the essence of all the languages in the training examples. They form a language model. The larger the model is, the more information it will store about the training corpus. It will capture the vocabulary, the morphology, the grammar of the languages, and more. Training large language models is computationally expensive, so over time there's been a trend towards pre-trained language models. Models are trained using only a few key objectives, say next word completion or masked language modeling, and that can be subsequently adapted, fine-tuned to other tasks. So a key paper in that space was the BERT paper. This was published by colleagues at Google in 2019. BERT is based on sequence modeling. It's bidirectional, so it considers context both on the left and the right. It has contextual representations, homonyms, words which have the same word has two different meanings, will have different representations for those different meanings. BERT uses transformers, which distinguishes from earlier work. There was a system called Elmo, which used LSTMs, which are a lot more expensive, and so therefore they could scale to larger corpora. Okay, and BERT has been widely used in the community. So the state of the art then continued to evolve rapidly. Just talking about Google, BERT was succeeded by a system called D5. D5 was succeeded by Palm. Palm was succeeded by Palm 2. Then Gemini, Gemini 1.5. They didn't write a paper for Gemini 2.0, but they wrote a paper for Gemini 2.5. This is really hot off the press. And at a high level, the thrust of research is on creating pre-trained models that are generative, obviously, multilingual, multimodal, understand images and video in addition to text and audio, multitask, and agentic. We have heard a lot about agentic systems at this KDD. So the other key ingredient next to document embeddings is term vector databases that actually then allow you to find related documents, so documents that are related to the semantic representation of a query. And so here on the left is a paper from 2013 that was one of the first papers in that space. There has been a lot of work on this since then. There are many commercial entrants. There is a company called Pinecone. There is another company called Weaviate. You can buy term vector databases as a service. There are open source implementations, and so this is the key ingredient. And I should mention that those industry-grade systems, they are today distributed, fault-tolerant, they scale to billions of vectors. So pretty much, unless you're Google, you can cover your entire corpus. So the architecture of A semantic retrieval system is very similar to a lexical retrieval system, except that you replace the index by a vector database, and when you crawl documents, you will embed them into the embedding space, and when you perform a search, you will go to the embedding server and find the key nearest neighbors of the representation of the query. And so in this model, there is no need, or at least less need, to do any synonym expansion. So to recap, here are some key differences between lexical and semantic representations. In the lexical space, you have a high-dimensional space. The space is as big as the vocabulary of the language, so you should think billions of words. In the semantic thing, you have a low-dimensional space, think hundreds of real numbers. The left one is sparse. Most documents will not contain a billion words, they will contain maybe 10,000 words. The right one is dense. Pretty much all the numbers in the dense representation will be something other than 0. The left is based on this term vector model where terms are uninterpreted. The right is based on distributional semantics where words actually have meaning. Inverted indices are computationally cheaper than term vector databases, both on the indexing side / embedding side and the retrieval side. It's still easier to scale inverted indices. And the inverted index doesn't have an explicit language model, so you don't need to worry about updating such a model. But there is a caveat that the synonym expansion model and the ranking models will typically do have their own separate language models, which you do need to update occasionally. So here is the architecture of a hybrid system where you combine a lexical system with a semantic system. When the query arrives, you will send it to both the embedding server and the index server. Both of them will return results. You will merge the results in some fashion and then get the snippets and return the results. Why would you want to do this? Well, it turns out that lexical systems are still superior at answering precision queries. Assume you have a query about a particular part number, and there is maybe 3 documents in the web that have that part number. A semantic index would not surface those 3 documents, but the lexical index will. So commercial search engines still rely on lexical indices. Here is a plug for a paper that I was actually a part of. So we evaluated the effectiveness of such hybrid systems. We did this using open source technology and an open source data set, namely the track newswire data set. And we found that indeed the hybrid system performed superior to the individual systems. Okay, so moving right along, so far we have talked about how classical information retrieval systems have evolved, and how language modeling has brought about more sophisticated systems. So now we're going to talk about how that same progress enables a new kind of information seeking experience where questions are answered directly. So NLP researchers soon observed that language models not only absorbed the vocabulary and grammar and morphology of a language, but also memorized basic facts about the world, facts found in the training examples. So colleagues at Google set out to quantify actually how much factoid knowledge is contained in the parameters of such a model. And they did this by pitting a closed box system, which was a fine-tuned version of T5, or actually multiple versions of T5 of varying sizes, against 9 systems that were traditional extractive question-answering systems, not generative, and open book, so they could retrieve stuff from the same corpus. And the results were very encouraging. The largest T5 model, just relying on its parametric memory, performed not quite as well as the state-of-the-art extractive systems, but quite competitively. So inspired by this, colleagues and I wrote a paper, this was in 2021, that said that there is a new way of answering questions. Language models can be used to answer questions directly in a generative fashion, and that's a superior approach to traditional search. And we argued that such an approach would lower the Delphi cost. The term Delphi cost hadn't actually been coined yet, but that's the essence of our argument. And so we laid out a couple of key desiderata that such a system should have. First of all, it should be reliable. That means it should only draw on authoritative sources when generating an answer. It should not hallucinate. It should also remain faithful to the sources. In the process of generation, it shouldn't twist the words. Second, it should be transparent. That means it should be able to attribute particularly parts of the answer to source documents, to evidence in an underlying corpus. Here the inspiration was Wikipedia, where you're expected to have an annotation pointing back to a primary source. Third, the system should be unbiased. That is, it should avoid surfacing societal biases that might be present in the underlying corpus. And this is clearly a very difficult objective, right? Because as we can see in political discourse today, I mean, there is no agreement on truth. There's no fact, just interpretations, as Nietzsche said. But with that being said, the system should be able to at least give multiple sides of an argument, and it should not go into fringe opinions. And finally, the system should be accessible. That means it should be able to give answers in a way that is understandable to the user, obviously speaking the language of the user, but also adapting itself to the knowledge level of the user. Again, that's an inspirational goal. It, for one thing, requires knowledge of the user. So next I'm going to talk about the evolution of retrieval-augmented question answering systems. We discuss some key challenges and compare these systems with the alternative of closed-book systems that don't rely on external memory. So open book question answering means that the question answering system can draw on external memory, such as a search engine. In 2020, colleagues at Google described a system called Realm. Realm was not generative, it performed extractive question answering. It had two components, a retriever and an extractor. Given a question, Realm would map the question to an embedding using BERT. It would retrieve a set of documents from a term vector database, in this case, a thing called SCAN, which is a Google internal database. Then it would use a span prediction model to find the passage in the surface result that would answer the question. It would rank the various passages that were extracted and then return the passage that was overall deemed most relevant. And it's important to stress that the system can be optimized end-to-end. Every portion of the system is differentiable. So Realm was evaluated on multiple open domain question answering benchmarks and did well. Please read the paper for detail. So inspired by this, a team at Facebook AI Research built and tested a generative equivalent, which they called Retrieval Augmented Generation, or RAG. The paper is right here. So RAG has a neural retriever just as Realm does, but while Realm retrieved entire documents and then performed passage extraction at inference time, RAG does the passage extraction at indexing time, indexes passages, and then at inference time doesn't need to perform passage extraction. And so each candidate passage is fed along with a query to the generator, and then the generated answers will be ranked according to the predicted relevance and the most likely answers returned. Again, in RAG, every part can be jointly optimized. So retrieval augmented generation uses external memory to guide the generation process, the inference process. So in other words, that part leverages both parametric knowledge, what is in the model, and external knowledge, what is in the index. In the FAIR system, those two things were not coupled. The generative model is trained without leveraging the retrieval mechanism. Colleagues at DeepMind explored bringing retrieval into the training process. So they built a system called RETRO, which stands for Retrieval Enhanced Transformer. And there, during the training process, each training example was enriched by documents that were close to that training example in semantic space, would be appended to the training example. And then during retrieval, RETRO would also rely on external memory that was about 1 order of magnitude larger than the external memory used during training. And there was a bunch of other innovations in there. And they scaled this to an extremely large memory, 1,000 times larger than was done in Realm and RAG. So for more details, see the paper. So at about the same time at OpenAI published a paper on WebGPT. WebGPT was a system for long-form question answering using GPT-3 as a generative model, and the Bing web search engine is retriever. So in other words, it was again retrieval augmented. And WebGPT is tightly integrated as a web browsing environment, and it can act as a search companion. OpenAI used this to actually collect human relevance feedback from paid workers. Paid workers were given a question and asked to search the web to find potential answers and then to write an answer. And these answers are, these question-answer pairs are called demonstrations, and they were used to fine-tune GPT-3 to do the same. And then independently, WebGPT can also be given a question and asked to generate 2 alternative answers, and the paid rater is asked to judge which answer is better. That's a lot easier for humans than writing a new answer. Comparison of 2 alternatives is an easier task. And because of this, you can collect a lot more of them. And so this paradigm of collecting those human labels and then feeding them into an IL system to, get a reward, became then known as reinforcement learning with human feedback. WebGPT predated ChatGPT by about a year, but it received only limited attention outside of our community. And then a month after that, colleagues at Google, a small army of them, published a paper on Lambda, which was a large language model that was specifically designed for dialogue applications. Lambda, given the question, would consult external knowledge sources, such as Google, and then generate potential responses, which were then filtered for safety, grounded on external knowledge sources, and re-ranked to find the highest quality response. And the paper introduced a whole number of key metrics for evaluating such systems: quality metrics, safety metrics, grounded metrics, informativeness metrics, and so on. Again, please take a look at the paper if you find this interesting. Okay, so one key challenge is the faithfulness of answers. Ideally you would want to have truthfulness, but as I mentioned earlier, truth is an elusive concept, so just being grounded on the source in the underlying corpus, we will settle for that. So a bunch of colleagues at Google introduced this notion of knowledge-grounded dialogue. They had 3 key requirements. The generated answer should be written in objective voice, as opposed to be a personal anecdote. They should have high lexical overlap with an underlying piece of evidence, and they should be semantically entailed by the evidence. So they fine-tuned 2 data sets on a grounded generation data set, and they evaluated this on a benchmark called the Wizard of Wikipedia, and the system performed much better than the baseline model. And then the other key challenge is attributing an answer to underlying sources. So there is another paper, the RAR paper, which stands for Retrofit Attribution Using Research and Revision. In this framework, after having generated the answer, the system would extract queries from that answer, issue them to a retriever, get documents which were responsive to this query, and then check if the portion of the answer that gave rise to the query was entailed by the retrieved document. And then if it wasn't entailed, they would rewrite the answer to actually have the entailment come true. So this goes a long way to avoid hallucinations. Okay, so here is quickly the architecture of such a retrieval augmented system. And you can see the one new thing is that there's a language model at the top, and you train it, and you have a generator. Okay, so the alternative is a closed-book question answering system. I'm not going to belabor this too much. I will mention that early versions of ChatGPT were closed-book. Around 2023, ChatGPT started to use retrieval augmentation. In a closed-book system, you have a number of thorny issues. You can't perform grounding, so you have an increased risk of hallucination. You don't have transparency. It's difficult to attribute any utterance to an underlying source. it might not be as scalable as an open source, as an open book system, and knowledge evolves, but it takes months to train a model. And there was some work at Google that tried to address this. I'm not going to go into the details for reasons of time. And this would be the architecture of such a closed book system. Okay, so comparing the two approaches, so in a closed book system, you have the issue that it takes months to train a new model, whereas an inverted index, or for that matter, a semantic or term vector database can be updated within seconds. And indeed, if you use Google search, I mean, within a minute or so, a breaking news story will actually show up. It cannot, a closed book system cannot be trained on private or proprietary data for cost reasons. Can't afford to train a model for every user, every customer. But if you were to train a unified model on all of that data, you would risk information leakage. Whereas in an index, it's very straightforward to separate, to attach access control lists to documents. 5 minutes. Attribution of answers to training examples is difficult in closed book systems, whereas it's straightforward in open book systems. Hallucinations are an issue in closed book systems, not in open book systems. On the plus side, closed book systems can be trained end-to-end. In the open book system, inverted indices certainly can't be trained end-to-end. They're black box. Okay, I need to speed up here. I'm running out of time. I'm going to talk very quickly about tool use. We heard earlier on today in the keynote that, I mean, systems are poor at, large language models are poor at doing arithmetic. So some colleagues at Google had the idea of equipping BERT with a calculator. And so the key idea is that when given a question, you would extract numeric quantities from that question, treat them as the operands to a computation, figure out what the operator should be, addition or subtraction or multiplication, and then issue it to a calculator, get the response, and incorporate it into an answer. And I mean, tested on the drop data set, which is a discrete reasoning data set with a lot of arithmetic problems, this gave a 50% increase in performance. So you can generalize this into tool-augmented generation, where the system can use arbitrary tools. For example, you could imagine using a set solver. Here is a key paper that describes such a system. The learning task is given a question, figure out what the input of the tool should be, and then given a tool output, map it to an answer. And in this paper, they do train those two mapping functions using a bootstrapping approach. First, they will have a small set of quadruples of input, tool output, quadruples. And then they will have a much larger set of just question-answer pairs, and they'll use some form of iterative self-improvement to basically brute force their way to find the right operators in the system. And for that, it's of course important that the system does have a finite space of operations. Here is a survey paper by colleagues at Meta on tool-augmented generation. My meta takeaway from this is that language models are the new middleware. They are great at gluing components together. Okay. So next I'm going to talk about reasoning. The type of reasoning that you need to answer complex questions. So the standard way to adapt the pre-trained language model to a new task is to collect a set of question-answer pairs and then to fine-tune the model, and that's very expensive. So an alternative, which was thought up by researchers at OpenAI, is to put some examples of related questions and answers into the context, in the prompt of that is given to the generator. And it turns out that this goes a very long way. This will be a lot better at coming up with well-reasoned answers. So this is dependent on the length of the context window. The initial work was done on a system that had a context window size of, I believe, 2,000 tokens, 2048 tokens. Today, like Gemini 2.5 supports, I think, 10 million token context windows. They can put a lot of training examples in there. And actually, putting in a lot of examples does help. There's a paper describing this. There is some evidence to the contrary as well. There is a lost in the middle effect, that stuff in the middle of the context window is less likely to be picked up than stuff at the beginning and at the end. Moving right along to chain of thought prompting. So in 2022, colleagues at Google suggested an improvement to in-context learning. Rather than providing the model with a few examples of task-related questions along with their final answers, also at the reasoning steps that were involved in producing the answers. And this causes the model to perform similar reasoning steps for the actual question. This is called chain of thought prompting. It works well on problems that require some form of reasoning. So this is mind-boggling. So researchers at the University of Tokyo and a team at Google found that you could actually do zero-shot chain of thought prompting. Rather than giving the system a bunch of reasoning steps, examples, demonstrations, you could just say, think really hard, take your time, and the system would perform much better than if it wasn't given that instruction. I find this completely magical. So another way to improve chain of thought prompting is to generate multiple responses, and you can do this very efficiently by just on your beam search, explore multiple paths in the beam, and then at the end do a majority voting between the answers that are most consistent along that have a plurality along the various paths. Return one of those. Another technique is to decompose hard problems into easier subproblems. This is called least to most prompting. Again, this is done by putting demonstrations into the prompt. And this advanced the state of the art on a range of reasoning problems, including arithmetic reasoning benchmarks shown in the table on the bottom right. I think I'm running out of time, so I'm going to fast forward a little bit. I want to talk a little bit about challenges to the web ecosystem. So this is the final chapter of my talk. So I'm going to talk about the challenges that are brought around by generative models. So generative models change the nature of authorship. We all use generative tools to help us write better. I mean, it's built into your email systems these days. And that's not a bad thing. I mean, the reader is helped by having fluent prose. It becomes a problem when the entire content is produced wholesale. Today there is an industry of content farms that is in writers in low-wage country producing, basically having paper mills, content mills. And this industry is embracing Gen AI wholesale, right? I mean, there's a lot of machine-generated content out on the web right now. And if you train on machine-generated content, you risk something called model collapse, where the model will actually not be reflective anymore of like the distribution of human language. So second of all, direct answers have the potential to reduce clicks on results in search engines, and thereby reduce the amount of traffic that is directed to websites, which affects their economic viability if they're financed through, say, ads or affiliate marketing links or what have you. And then finally, direct answers affect how users interact with search engines themselves. If they don't click on results, they will probably also not click on ads, right? So there is an economic problem for search engines itself. Okay, so how much time do I have? 1 minute? Okay. Very quickly, here's a paper by people at a variety of universities that talks about model collapse. They took a model and recursively trained the model on its own output, subsequent generations of that model, and they found that after 10 rounds or so, the 10th model would have very little resemblance to the first model. They attributed this to two flaws. One was that the sampling process takes out the tail ends of the distribution. The other one was that the choice of the network, the neural network architecture will limit what exactly you can learn. So the takeaway here is that we want to train on human-generated content, so we need a technique for identifying human-generated content. And there is some techniques on this. Here's a paper from Stanford that does exactly that. It doesn't work very well. So this particular paper assumes that you have access to the model that generates the content, and that works well in a world where everybody is an honest player and all the different GenAI companies provide an interface, but there will be rogue entities. And so this is a very difficult and very important problem. Here, this is about how direct answers affect referral traffic. The pessimistic view is that if people will not click on attribution to verify that the result is true, that there will be a drop in traffic to content providers. The optimistic view, of course, is that the people who do click are much higher value customers and might actually then transact on that website. I think realistically speaking, there will be some diversification in revenue streams for content providers. Okay, so just to recap, here is a timeline of some, not all of the papers I talked about. You will notice there are different scales. The top scale is in decades, the bottom scale is in years. I think progress has sped up tremendously. I'm super excited. And then I will conclude by just giving you 4 key takeaways. So direct answers lower the relative cost of information seeking. Their generative models are a key enabler for direct answers, and they provide critically the information to fuse together information from multiple sources. There has been great progress on grounding answers and attributing them to sources, and benchmarks for that are being developed. Longer-term systems become more stateful. We heard about this earlier today. They will remember past interactions. They may have a model of you as a user. And they will leverage tools that go beyond information-seeking tasks to be able to perform transactions on your behalf. And then finally, and most importantly to me, that classic information retrieval is not dead. External memory, such as a search engine, remains indispensable. Semantic retrieval is a vibrant research area, and there is a whole new frontier on rethinking various parts of the information retrieval pipeline for GenAI. Like ranking and passage extraction. And with that, I'm open for questions.
Hi, Jeff Pan from University of Edinburgh. Thanks for a nice talk. You mentioned that the long context language models is really promising, and you might also mention that there are some issues, for example, loss in the middle for single hot question answerings, and recently there's also some new discoveries about multi-hop question answering. It's called loss in between. So what's your visions about this kind of a long context language model to see whether they could address those issues?
Here is the truth. I don't actually know how the 10 million token context window works in Google, right? I mean, in the normal transformer architecture, you have self-attention, which is fundamentally quadratic. And then there were papers like the ETC paper, the long T5 paper, that said, well, we have a local small context and then a global context of a few key tokens, and then we do comparison between this global pool and each local occurrence, and then a small context window. I don't know if it's still the same. Obviously, the heuristic you are using to deal with long context will affect things like how much attention is paid at each position of the context window. And my guess is that the lost in the middle effect might be an artifact of that. It's more pronounced for very long contexts.
What about the multi-hop setting? I suppose that is kind of more interesting for people in the conference, where you need to do multi-hop reasoning, and
I'm sorry, I didn't quite acoustically hear the question.
Yeah, I was saying that for multiple question answering, there is some additional issue for long context language models called loss in between. For example, the evidence
multi-turn conversations. Yes. I guess it depends on how long the conversation goes on, right? So I did read an article where, in a setting where GenAI was used for code generation, every once in a while the amount of state is being compacted, and that is catastrophic, right? I mean, at this point, suddenly code that comes out is garbage. So I think that those applications will suffer more from it than human-machine conversation, because fundamentally we will input only yay much, right? Less than 10 million tokens.
Yeah, thank you.
Hey Mark, thank you for the talk, super engaging. So I want to double click into the RAG part a little bit and maybe like a thought and then a question. The thought is with GenAI, it is, totally agree, critical to have tool use. But I think one thing that I think it's important, but you didn't quite mention it, and I'm curious to hear your take, is to have a reliable index. So
to have what?
A reliable web index. So I mean, I think it's only going to work if you actually have a index at Google size, where you actually know, okay, well, you pretty much index basically most of the web pages, and then okay, well, you can call that. So yeah, I guess what's your take on that? Like, is that what you've seen at work, and how important is that? And then related to that is about hallucination. What's your take on that? I don't think we can quite eliminate it entirely, but does it really matter? What's your thinking there? Thank you.
So I agree that Google has a very large index. It does not index the entire web. That's a design choice. There was a decision to, cap it at a certain point, which makes sense because the web is actually infinite. There's so much content that is being generated on the fly as you visit a particular URL. I do believe that you don't need 100 billion web pages, or whatever the number is. If you were to limit yourself to 10 billion quality pages, it would be good enough. And I think that there are a lot of entities that could put up a competitive offering. I mean, before I joined Google, I worked for Bing, and
And then on hallucination, do you have any thoughts or things you want to share?
On how people outside of the search engines could have access to a high-quality index?
No, just slightly different, slightly unrelated. In that we're doing retrieval, and I guess in moving from a classical retrieval system to a more GenAI-backed retrieval system, does it really bother you that there was always going to be risk of hallucination, or what's your thinking there?
Yeah, it does bother me. So the work on post-generation grounding is very crucial in my mind, that you are always able to attribute any claim in an answer to an underlying document, and then ideally either filter on the reputation of the source, or at least make the reputation of the source explicit. I mean, you can figure out if a source is reputable or not, right? There's many measures for that.
Okay, thank you.